Welcome to Calculus 1. I want to start by giving you a quick preview to what we're going to be doing in this class. Calculus is the mathematics of change and accumulation. So for example, in algebra, you worked a lot with functions and relationships between variables. You might want to know what is the position of a bicycle after, say, 5 seconds, and you could read that information from a graph or perhaps use an equation to solve that problem. In calculus, I am interested in how is the position of that bicycle changing, or in other words, what is the velocity of that bicycle at any instant in time. I can compute that velocity or that rate of change by computing a slope. And the slope I want to compute would be the slope of a line tangent to this curve. So one of our important calculus problems is going to involve computing slope, specifically slope of tangent lines. The second problem we're going to look at is going to involve total accumulation, or in my example, imagine that we have an object that's moving with a velocity that's not constant, so it doesn't have a constant speed or direction. We might want to know the total distance that object has traveled. That is a calculus problem, and it's going to involve computing the area underneath that velocity function. So my two really important calculus problems involve slope and area. Let's take a closer look at both of these problems. In the slope problem, we can start by thinking about average rate of change, and that's something that you probably have seen in an algebra class. Maybe you use different words or different notation, but I have a function graphed in red, and I can create a line that connects 2 points on that graph. The slope of this line will give me my average rate of change of this function. So in this case, my line goes through the point 2, 8, and 5, 12.5. The slope of that line is just going to be rise over run, or change in y over change in x. In this case, my change in y is 4.5, my change in x is 3, and so that means my slope, or average rate of change, is 1.5. I can do this for any 2 points on this curve. So now if I look at the point, same point 2, 8, but let's make our second point 4, 12. If I compute my slope, my change in y over change in x, this time I end up getting 2. So my average rate of change is now 2. And the idea is we can take that second point and move it closer and closer to our first point. So now I'm at the point 3, 10.5, and I compare that to my point 2, 8. I get a slope of 2.5. And I'm going to continue doing this process. I'll make that second point even closer to my first point. So 2, 8 and 2.5, 9.375. What is the slope there? Again, I just did change in y over change in x, and this time I got 2.75. And as we make these 2 points closer and closer together, that is going to give us an idea of what is the slope of our tangent line, or what is the slope of a line that just touches that point 2, 8. And the slope of our tangent line is actually going to be our instantaneous rate of change. That is what we're really interested in finding in calculus. That's something that's known as our derivative. So we're going to spend a lot of the semester talking about finding derivatives or slopes of tangent lines. The second calculus problem involves area. So for example, if I wanted to find the area underneath a curve, and I have an object where I can't just use a formula from geometry, well, how do I do this? One way to do this is to take the region and chop it up into rectangles. And we can approximate the area underneath this curve by drawing rectangles, computing their areas, and adding them together. And so in this case, I use 6 rectangles, and at the bottom of the screen, I have written down the area that I computed. I had my computer compute it for me. I got a little over 4.5. And the idea is if I increase my number of rectangles, so now I've got 10 rectangles, my area approximation should become more and more accurate. And so now I've got 20 rectangles. My area is pretty close to 4.5. And you can see with those 20 rectangles that the area that we're computing is actually pretty close to the area under that curve. And I can actually keep going. I could do 100 rectangles, and my area is even closer to 4.5. Just based on this, I'm guessing the actual area under that curve is probably 4.5. So the idea is we can use rectangles, and if we increase our number of rectangles, we'll get a more and more accurate answer or estimate for our area. The calculus problem is going to involve, well, how do I compute the exact area under that curve rather than just estimating it? And so that's our second really important calculus problem. And finally, it turns out that these two different calculus problems, finding the slope of a tangent line, which is an instantaneous rate of change, and finding the area underneath a curve, which is a total accumulation, these two calculus problems are actually related to each other. And so these are the topics that we're going to be diving into this semester. We'll spend a lot more detail talking about exactly how to solve these problems, but I just wanted to give you a quick overview of the big picture of calculus and what we're going to be doing in this class. I look forward to working with you this semester.